come in.
Yeah, let's do that. So I've muted everyone. I will unmute everyone or allow everyone to unmute after the talk. And yeah, recording's on.
Great. Okay. So thank you very much, Christoph, and thank you today to our speaker, Victoria Stevens from the Earth Observatory of Singapore. Especially thank you to you because it is very late in the evening there right now. So this is an 11 p.m. talk for you. Just to give you a very short biography of Vicky's progress. She started off in Cambridge in the UK doing her undergraduate degree, and then did a PhD in Caltech under the supervision of Jean-Philippe Avouac. And after that, spent 1 year in Nepal working for NSET, building earthquake hazard models for Nepal, a year with RMS, Risk Management Solutions in London. And then after that, returned to academic post in University of Cape Town, South Africa. And then since September, just arrived in EOS as a senior research fellow. Vicky's going to talk to us today about the relationship between strain rates and seismicity in the India-Asia collision zone with implications for probabilistic seismic hazard. I'm very much looking forward to hearing this. We will have some time for questions at the end. So Christoph will kind of take over at the end again. You can put questions in the chat box or we'll find other ways of doing it. Okay, over to you, Vicky. Thanks again.
Okay, thanks, Richard. So today I'm going to talk about a project which I actually began at Caltech and then left for a few years. And then I started up the project again when I was at Cape Town, but I was still working with Jean-Philippe Avouac. And this talk is based on a paper that came out in JGI about a year ago. So in this talk, I'm going to come up with a new, fairly simple method for probabilistic seismic hazard analysis. And I focus on applying it to the India-Asia collision zone, though it could potentially be applied in many other areas with a few caveats that I'll talk about in my talk. First, I'll talk about the motivation for this study. Okay, the main figure here is a probabilistic seismic hazard assessment map, and that's made by the Global Earthquake Model. So they have synthesized various publications about seismic hazard in different regions and tried to put them all together into one map, and they have a map of the entire world for seismic hazard. So if you're not that familiar with these plots, what it actually shows is peak ground acceleration. So that's basically a measure of shaking with a 10% chance in 50 years. So in a 50-year period, what shaking level will it reach with a 10% chance? As you can see, and as you might expect, over the Himalayan arc, there's a very high hazard, and in stable India and elsewhere, the hazard is much lower. In the region shown here, it's broken down into 4 separate areas, and that's based on the 4 different models that go up to making this map. In India, it's based on a paper by Nath and Thingbijam from 2012. And in their paper, they based the hazard analysis on tectonic areas. So they divided the entire region they were looking at into areas of similar tectonics and calculated the hazard for each different area. The model in China was done by the China Seismic Zoning Map. And in their region, they also looked at tectonic areas, but they also specifically input faults into their model. And that's why you can see some long linear areas of higher hazard in the Tibetan Plateau and its surroundings, because faults were specifically input into their model. And similarly for Southeast Asia and the Middle East as well, different studies were used and then compiled to make this map. And all the underlying studies have a slightly different methodology. and they can be hard to combine. These models from different sources, they do overlap at the borders, but sometimes they don't quite agree. These models also have lots of input data, such as the geometry of faults, the slip rates on faults. There's potentially a problem if you're missing some faults. They also rely on paleoseismicity, instrumental seismicity, and they do have some subjectivity when it comes to defining the tectonic source areas or which faults to include. Also, for all of the regions that you include in your model, you have to come up with various parameters that describes the seismicity. So if you do input a fault into the model, you have to be able to come up with some parameters I'll talk about later that describe the seismicity on the fault. So what I wanted to do was to design a simple method for probabilistic seismic hazard analysis that uses only geodetic data and seismicity. And the criteria I wanted my model to have would be that it's easily updatable. So as soon as there's new geodetic or seismic data, it can easily be input into the model, and the model should get better all the time. I also wanted it to be less subjective. So for the tectonic areas, not really to be made in a subjective manner, but objectively. And I also wanted it to be able to be applied globally. But before I started doing the actual modeling, there were a few initial questions that I needed to ask. The first one was, is our geodetic data good enough to actually make a model from it? So in my study here, I only use GPS data, though INSAR data would also be appropriate. And the second question was, is the seismicity uniform in both space and time? And I'll talk about those two questions later. First, we'll look at the geodetic data. The plot on the left-hand side shows a compilation of GPS data from the literature, and it basically shows India moving northwards and colliding, and over the Himalayas. There's lots of shortening, and then as you go further north, there's some extension east-west in the Tibetan Plateau. So this is a compilation of many GPS studies on the left-hand side. As if you look on the right, this is the strain rate map that I made, and this is based on the method of Carl Tape et al. 2009. Again, as you might expect, the areas of highest strain rate are firstly over the Himalayas along the Himalayan arc, and in most of India, the strain rate is much lower. If you look in the Tibetan Plateau, the GPS is dense enough to pick out some of these faults. You can see that the Altan Targ on the northern side of the Tibetan Plateau, and some of the faults around the edge of the plateau. If we zoom in on that area a bit more, now the black lines show faults from an active fault database of Styron et al. And you can see that the strain rate from the GPS does tend to follow the surface traces of the main faults in the region, which are labeled. For the main Himalayan thrust, the highest area of strain isn't directly corresponding to the surface trace of the fault. And that's because the high strain rate is further back from there, where the rate goes from very low in the Tibetan Plateau to much higher. And that's to do with the coupling, because the fault is locked for about 100 kilometers north of the surface trace of the fault, and that's where the strain rate is the highest. Okay, so now I'm going to look more at the strain rate data and whether it is actually good enough. A second question I'll ask is the strain rate constant over time? So on the left-hand side, it's a plot of the directions of principal strain rate, and that's based on earthquake moment tensors from the CMT catalog. So in red, you have maximum principal strain rate, which is showing compression, and in blue, it's minimum, which shows extension. So these are all from earthquakes on the left-hand side, and as you might expect, over the Himalayan arc across Nepal, you have fairly north-south compression because you have a lot of large thrust earthquakes there. As soon as you move slightly further than north into the interior of the Tibetan Plateau, you see east-west extension because you have lots of extensional grabens in the Tibetan Plateau. The figure on the right is the principal strain rates from the strain rate model based on GPS, and then sampled at the location of the earthquakes. So you can see in general, the pattern agrees fairly well. Again, over the main arc of the Himalayas, you have fairly north-south compression, and then extension, east-west extension in the Tibetan region. So the fact that the directions of principal strain rate agree between the earthquakes and the strain rate based on GPS tells us two things. Firstly, that the GPS is dense enough to distinguish different strain areas or different tectonic regimes. If we didn't have that many GPS points, the strain would be averaged out on a larger scale, and we wouldn't be able to see these differences, and it wouldn't agree with the earthquakes. Secondly, it tells us that the strain buildup from the GPS reflects the strain release on the timescale of earthquakes. So these, the GPS from the literature, some of them have only been recording for a few years, and the longest maybe around 20 years. So they only record the strain rate over the past 20 years. Whereas earthquakes, they have to have a much longer time of strain rate buildup before the earthquake actually happens. So they essentially sample the strain rate that has occurred over many decades, hundreds of years, even thousands of years. And the fact that our GPS, which measures over a shorter timescale, seems to agree with these earthquakes, suggests the strain rate recorded from the GPS is fairly constant over a much longer time period. So now we've seen that the GPS are okay. We're going to divide the entire region into areas of different strain rate. So this map is the same strain rate map from a few slides earlier, but now it's a contour plot. And it's been divided into 10 regions of different strain rate. Again, higher over the Himalayan arc and lower over most of India. There are some tiny dots plotted on top, and they're a declustered 10-year earthquake catalog. I'll talk about declustering in the catalog on the next slide. But these strain rate areas will form the basis of my seismic hazard assessment. So I'm going to ignore faults entirely and only going to rely on the GPS-based strain rates to define different source areas for the seismic hazard model. So now I'll move on to looking at the earthquakes. I used two earthquake catalogs. I mainly used a 10-year ISC catalog from 2010 to 2020. This is because there was a fairly uniform level of seismicity within this period. In the years before 2010, seismicity was increasing year on year because lots of new seismometers were being set out to cover the region. And in that 10-year catalog, there's almost 10,000 earthquakes. I also looked at historic earthquake catalog, 100 years of that catalog from Global Earthquake Model. So the seismicity needs to be Poissonian to go into our hazard analysis, because we need to use the seismicity to find the Gutenberg-Richter parameters, the A and B values, and they'll be input directly into the hazard analysis. So the A value is basically the activity of earthquakes or the overall rate of earthquakes, and the B value defines how many large earthquakes there are compared to small earthquakes within each region. So what Poissonian actually means, it means that earthquakes in time, they have a constant mean rate and they're independent. So they can't be aftershocks because aftershocks aren't independent, they're dependent on the main shock. So firstly, we have to decluster the earthquake catalog. And I did a few tests of this. I'm showing you one now, but we did some others that I'm not going to show. I used the declustering algorithm of Riesenberg, 1985. The figure on the left, it shows you the 10-year period from 2010 to 2020. And on the y-axis, the total number of earthquakes over magnitude 4. So for the entire region, I used magnitude 4 as the lower cutoff value, since the catalog seemed to be fairly complete above magnitude 4. The black line shows all of the events, and you can see there are a few jumps, and that's because when large earthquakes happen, like the Gorka earthquake, which is the dashed line labeled G, there were many earthquakes or many aftershocks after the main shock, so there's a big jump there. The declustered catalog is below in red, and that line is fairly straight, which we want it to be. Shows that we hopefully have only got independent main shocks in this catalog. On the right-hand side, it similarly shows how the declustering algorithm performed. Again, there's the date on the x-axis and now the latitude on the y-axis. And you can see clustering in the left-hand plot. The main cluster at about 28 degrees latitude is again the Gorka earthquake. And you can kind of see how the aftershocks continued a bit in time. The right-hand plot is the declustered catalog, and now you can see that these clusters have mainly disappeared. So visually, the declustering has worked fairly well. And now we can move on to looking at if the seismicity is Poissonian. Okay, so here I'm looking at if the seismicity is Poissonian in time. So I'm plotting the inter-event time between earthquakes above different magnitudes. So all the different plots show earthquakes above certain magnitudes. The top left plot is all the earthquakes above magnitude 4. And then the one to the right is all the earthquakes above magnitude 4.5, etc., up to magnitude 6.5. The top two rows show the 10-year catalog, and the lower row shows the 100-year catalog. So what these plots are actually showing is the time between different events. So all the events are ordered in time, and then you count the time between each subsequent event, and then plot the cumulative number. So in the top left-hand plot, as I said, there's almost 10,000 earthquakes, and all the earthquakes have a gap between them of more than 0. But and on the x-axis, it's in days. If you look at 2 days, an event time of 2 days, there are now only 100 earthquakes in the entire catalog that have a gap of more than 2 days between them. And similarly, there's only one time in the entire 10-year catalog is there a gap of 4 days between 2 subsequent earthquakes. The straight dashed line on every plot is what it would be if the catalog was followed entirely the Poisson distribution. So it was, and the Poisson distribution is exponential. So the y-axis here is logarithmic, which is why the dashed line, the Poisson's distribution, is a dashed line. Is a straight line. So you can see that for most of the data, which is the solid line, it fits the Poissonian distribution fairly well. As you go to higher and higher magnitudes, if you look at the magnitudes more than 6.5 in 10 years, the data plot is fairly jagged. And this is because there were only 9 earthquakes above magnitude 6.5 in the 10 years. But even so, they still follow the Poisson distribution quite nicely. And again, if you go down to the earthquake catalog for 100 years, they also follow the Poisson distribution very closely, which is good. I also did similar tests to show that they were Poissonian in space, because ideally we want the earthquakes to be uniformly distributed within each strain rate area. And They were uniformly within each strain rate area, apart from the areas of lowest strain rate. Okay, so now, now I've shown that the GPS and the seismicity data are fairly good, so we can use them to find input parameters for our seismic hazard assessment. As I said, our source areas are the different strain rate areas. So basically we have 10 separate strain rate areas, and we are going to look at the seismicity within each of the 10 different areas. And in this way, we'll try and find the A value, which is basically the activity or rate of earthquakes, the B value, the relationship between the smaller and larger earthquakes, and the maximum magnitude within each strain rate area. Okay, so looking within each strain rate area, the plot on the left, the colored points show earthquake rate versus strain rate. And as you might expect, the earthquake rate is much lower in areas of low strain rate, and the earthquake rate is much higher in areas of high strain rate. On this plot, there are two separate fits. The straight black line is fixed to be linear, and the gray line is a nonlinear fit, which is perhaps fitting slightly better. Though for the rest of the talk, I'm going to concentrate on the straight line fit and assume the number of earthquakes is proportional to the strain rate. If you look on the right-hand side, similarly, it shows the earthquakes split into all the different regions of strain rate. And you can, so the solid lines are the 10-year catalogue and the dot dash lines are the 100-year catalogues. And they coincide fairly nicely. And this plot shows that at every magnitude in the areas of higher strain rate, there are more earthquakes. At the bottom, I showed the equation of the straight black line and the left-hand figure, which shows that just the number of earthquakes per time is proportional to the strain rate. And if this is true, it actually has some interesting consequences for what the maximum magnitude earthquake might be in each region. And to look at that, I'm going to detour slightly and talk about moment conservation. So by moment conservation, I mean the buildup rate of moment should equal the moment release rate on the long time scale. Moment buildup rate can be thought of as the rigidity times the fault area times the slip rate. But I'm ignoring faults and slip rate and using strain rate instead. So the equation is equivalently the rigidity times the surface area times the seismogenic thickness, and then times by the strain rate and a geometric factor. And this equation is similar to those in papers by Bird and Liu and others. And this geometric factor it generally varies between 2 and 4. And it varies because it depends how the faults take up the strain, whether they're strike slip faults or dip slip faults, what angle they are dipping and what angle they are at compared to the direction of maximum strain. The moment release rate, it's per time, and it's the sum of the moment of all earthquakes, from very small earthquakes to the maximum magnitude earthquake, plus some aseismic processes. The figure below is an example of the Himalayas, and it just shows that the moment buildup rate is a straight line. It's increasing steadily year on year. But the moment release rate is unsteady, and it's mainly released in these large earthquakes, which happen fairly infrequently. So if moment buildup rate and moment release rate on this are the same, these two, the equations on the first line and the second line, should also equal each other. And this is plotted slightly different. This is kind of the same information, but plotted slightly differently. The graph is a Gutenberg-Richter plot with magnitude on the x-axis and the number of earthquakes per year on the y-axis. The red line shows the Gutenberg-Richter law. It's an A minus B times magnitude. and that's where the seismicity would fall. And then this blue line is the frequency of the largest earthquake needed to balance the moment buildup rate. It's slightly confusing to understand, but if, for example, the maximum magnitude earthquake you had was magnitude 5, if you follow magnitude 5 to the blue line, you'd need roughly 100 magnitude 5 earthquakes per year to balance the moment. Whereas if the maximum magnitude was 8, if you go up from 8 to the blue line, you see a magnitude 8 earthquake, you'd have to have 1 per roughly 10,000 years to balance the same moment buildup. So this blue line shifts up and down depending on the moment buildup rate, and the red line can shift up and down depending on how much seismicity you have within each area. At some point, these two lines will intersect, and where they intersect, it will tell you the maximum magnitude needed for this specific region to balance the moment rate. Okay, and the equation of the lines where they intersect, for the red line, for the Gutenberg-Richter law, the number of earthquakes there is A minus B times the maximum magnitude earthquake. The blue line, the equation is more complicated, but the important things are that it contains the maximum magnitude earthquake, the moment buildup rate, and the fraction of moment released seismically, and then the B value. So since the left-hand sides of these equations are the same, then we also know that the two right-hand sides of these equations are the same. And what we want to do is rearrange the two right-hand sides to get what Mmax is going to be. So that's this top equation. Again, the details aren't that important. We've balanced the moment buildup rate and the moment release rate. And we see that Mmax depends on the B value, alpha, which is the fraction that's released seismically, the moment buildup rate, and the A value. However, the A value and the moment buildup rate can also be rewritten in terms of strain rate, and the area of the strain rate region, and B. So again, similarly, this is the Gutenberg-Richter law. Log the rate of earthquakes is A minus M times B. And we also know from previously, from the linear relation between strain rate and earthquake rate, that the earthquake rate is some constant times the strain rate. So if we substitute the number of earthquakes, that rate, if we substitute that into the left-hand equation, we're going to find a new equation for A that's only based on strain rate, the area of the strain rate region, and B. Similarly, from before, we already showed the moment buildup rate in terms of rigidity, this geometric constant, the seismic thickness, and the area of the strain rate region and the strain rate itself. So now into the top equation, we can substitute M dot and A, and it becomes this equation down here. So the important things to note here, in the positive log in the middle of the equation, there's a strain rate area A and strain rate. And there's also a negative log that also contains the strain rate and the area. So these actually cancel out the strain rate and the area of the strain rate region. So now we have the maximum magnitude earthquake, and now it only really depends on the B value. It doesn't depend on the strain rate or the area. It might be slightly counterintuitive at first, though if you have a higher strain rate, yes, you have a higher moment buildup. But if you have a higher strain rate, you also have a higher moment release rate because there's more earthquakes all the time. And that's why the maximum magnitude earthquake doesn't depend on the strain rate. Again, here, this is basically summarizing what I just said. The maximum magnitude isn't dependent on the strain rate or area. However, it does depend on the B value, the fraction of moment released aseismically, a geometric constant, the rigidity, the seismogenic thickness, and this constant of proportionality between strain rate and earthquake rate. So in the specific region that I looked at, I found that for all areas, the maximum magnitude earthquake should be between 8.7 and 9.4. But then if we think about recurrence time is not independent of strain rate and area. So here we see that the recurrence time in this equation, we have the A value, and the A value does depend on strain rate and area. And in this region, the recurrence time for the maximum magnitude earthquake varies from 500 years to more than 2,000 years. And actually for the area that I looked at, the areas of low strain rates have the shortest recurrence time because they're just very large areas. So it might be slightly counterintuitive because you might expect there to be more commonly large earthquakes in areas of high strain rate. But if all the assumptions I've said so far hold, then in the areas of low strain rate are very large, so they actually have the shortest recurrence time. If you look at, again, at the equation for A, if you double the strain rate and half the area, the recurrence time will be the same. But if you double the strain rate and the area decreases by 3 or 4 times, then even though you have a higher strain rate, the recurrence time will be longer. Okay. So now we actually come to the input parameters for the probabilistic seismic hazard analysis. We have all the different areas defined by the strain rate, and we calculate the A value for each rate based on this equation, which involves the strain rate and the constant of proportionality between the strain rate and the earthquake rate, and it also depends on the area. The B rate, we found a B value of roughly 1.06 for all the different regions. They all seem to have a similar B value. There are some fairly large uncertainties on this B value that go into the model. And then we also found a similar maximum magnitude earthquake for all the different areas. So if we put that all together, these are the results. And I used the software called OpenQuake to perform the probabilistic seismic hazard analysis. And that's free to download for anyone if anyone wants to use it. So here again, I'm showing the peak ground acceleration with a 10% chance in 50 years. It varies from basically 0. A lot of India has a very low hazard. And then along the Himalayan arc and further to the right, there's a fairly large peak ground acceleration. And this map is basically the pattern of this map directly reflects the pattern of the strain rate map. Apart from the small details that you can see quite well in India, the small little details that look a bit like rivers or something, they are from the VS30 values. So this is a site characteristic, and it's the shear wave speed the average shear wave speed in the top 30 meters of the Earth, which alters the pattern slightly. But overall, the entire pattern just comes from the different regions of strain rate. So now if I compare that again, the color scale is slightly different. Now this is to fit the global earthquake model on the right-hand side. And yeah, my study is on the left-hand side. So, so in my study, it's entirely based on areas of different strain rate and the earthquakes within those different areas. I completely ignore faults, the geometry of faults, slip rates, paleoseismicity, all that stuff I completely ignore. Whereas the GEM model on the right-hand side does include, or the studies that went into this model do include slip rates, geometries, lots of things. However, even though they're based on 2 kind of completely different, fairly independent, not fully independent, but fairly independent data sets, the end results look slightly similar. You can see in my study, you can kind of see some of the faults on the Tibetan Plateau, the areas of higher strain there. and the obvious area of higher strain along the Himalayan arc, and then a lower strain in India and elsewhere. I'm now also going to compare my study with a study I previously did in Nepal. So we're going to zoom in on Nepal now and compare my results here, not with the GEM model, but with a study I did previously. So here's the current study zoomed in on the left-hand side, and the right-hand side picture is a study I did in 2018 of Nepal. And this study the study on the right-hand side does include fault geometry and earthquakes. And before comparing these two studies in more detail, I'll quickly show you what went into my study from 2018. So this is some of the input data to my 2018 Nepal study. So in the top right-hand figure, that shows different, the source areas and faults. I specifically input the geometry of the main Himalayan thrust, and the different shades of pink show the ramp and flat geometry of that large fault. The Karakoram fault, I also specified as a fault, though these other regions were just put into the model as areas. And how I decided on what these areas of similar seismicity would be is partly based on the focal mechanisms from the CMT catalog you can see on the left-hand side, especially the intraplate earthquakes. On the right-hand side of the figure, you can see some deeper strike-slip earthquakes, and that goes into defining what I call the east region on the east-hand side. And you can also see some extensional normal faulting on the edge of the Tibetan Plateau, and that helped define the grabens on the edge of the Tibetan Plateau. And also I used the location or the surface traces of active faults, again, based on the Styron fault map. On top of that, I used what people call in papers expert judgment, but it's basically just me deciding based on the few things I just discussed. And then for each of these regions, I use various different catalogs, including historical and paleoseismic data, to come up with the A, B, and Mmax values. So going back to the two different studies, to compare them both, in the current model I just showed, I used, to define the source areas, I used GPS-based strain rate areas, whereas in my previous study, I used some known fault geometries. That was for the main Himalayan thrust and the Karakoram. And for the other areas, I used the CMT catalog fault traces and just kind of me deciding to define areas of similar tectonics. To get the source parameters in this current model, I used the model of strain rate versus earthquake rate, which was based on the 10-year earthquake catalog in each different area of strain. Previously, I used various earthquake catalogs on each fault or within each area and paleoseismicity. For the maximum magnitude in this study, I looked at conservation of moment between the strain rate buildup and the strain release from earthquakes in each area. Whereas previously, for the main Himalayan thrust, I had a conservation of moment between a GPS-based coupling model and earthquakes. And for the other regions, I studied a few things to estimate the maximum magnitude earthquake. The things I looked at were the largest earthquakes in catalogs in those regions, also scaling relations such as the maximum length of the fault and therefore the maximum magnitude earthquake, and also largest earthquakes in regions of similar tectonics. So there's quite a lot of differences between these two models, and the results are fairly similar, though with some differences. In the right-hand model from 2018, there is higher hazard. The area of highest hazard is slightly further south than in the current study, and it's also slightly higher. And that's mainly to do with the fact that the geometry of the fault is defined, and the earthquakes that occur are constrained to lie on that fault plane. And the fault is much shallower in the south And that's where you get the higher areas of shaking above the shallower parts of the fault. As on the left-hand side, the geometry in the fault, nothing to do with that has been input. And actually earthquakes have not been constrained to go in any specific direction. So if an earthquake occurred at a specific location, it could rupture north-south or east-west or any other direction. It is not constrained to lie on the main Himalayan thrust real geometry. And it's also slightly further north because it doesn't know that the fault is shallowing towards the south. Okay, and then basically I have my conclusions. So I showed you a new probabilistic seismic hazard method that was based only on GPS and earthquake catalogs. There are some advantages. It's quite simple. It's easily updatable. So as the length of the seismic catalog increases or the length of GPS measurements increases, it's quite easy to update and make better and better. It's also less subjective when it comes to defining the faults or source areas to include. So that's another advantage. You don't need any knowledge of fault locations or slip rates or anything to do with faults to perform this method. And also seismic gaps aren't a problem, or blind faults aren't a problem if you have enough GPS. You only need the average seismicity within a strain rate area and a good strain rate map to perform this analysis. However, there are some significant disadvantages. The main one, I guess, is it does ignore known information like the fault locations and slip rates. We do have a really good source in some areas, and for some faults, we do actually know their geometry, we know their location, and we have a fairly good idea of the slip rates and coupling maps and everything like that, which my model completely ignores. So it's not necessarily the best thing to do to ignore that good data that we have. It's not actually very good for low strain rate regions. This is partly because there aren't often many GPS stations in strain rate regions, which is why everyone assumes they're all low strain rate. And also the aftershocks in low strain rate regions last a long time. And so declustering doesn't really work very well. You also do need a good GPS and earthquake catalog to perform this analysis and make sure they pass the tests that I mentioned earlier on. And the strain rate areas need to be large enough to record average seismicity. You can't decrease the strain areas to be really tiny, else you won't have a good record of the average seismicity within each strain rate area. So there is a limit on how detailed the hazard analysis can be, just based on the number of earthquakes that you need to record an average seismicity. Though over time, as the length of the seismic catalogs increase, then you should be able to go to smaller and smaller strain rate areas. Okay, and that's the end of my talk. I'm happy to take any questions from anyone.
Thank you very much. That was really, really cool. Thank you. Thank you, Vicky. I'm sure we'll have some questions. Christoph will probably take over. I've got one question I can start off with. Christoph, are we going to ask people to put in the chat box or just ask their questions, or what should we do? People are raising hands, so we can do that.
So 3 options. So either you raise your hand and then can unmute yourself when I ask you to do that, or you just type the question in the chat, I think. Yeah, whatever you prefer. So after Richard, I've seen already there are raised hands.
Great. So there's one after me. So Vicky, thanks very much. My question was actually a little bit on because you were saying how things don't work so well in low strain regions. Where is that limit? I saw in your map you had areas such as the northern Tian Shan, which, and some of our audience are from Kyrgyzstan, Kazakhstan here, which in some ways is a kind of, you might think of it as a low strain region, but it's also there in your map. Also, if you look at the historical earthquakes from that kind of place, it does seem to be quite clustered. You know, you have these big bomb of magnitude 8 earthquakes in the in the late 19th, early 20th century, and then very little. And so where is the limit in terms of how you can use this, or where you think it's a method that you can apply?
Yeah, I guess there's one plot that I didn't show, but it's to do with whether the earthquakes were Poisson in space rather than time. And I didn't show it because it's slightly complicated. So these are for all the different strain rate regions. The y-axis is Ripley's K function, and it's a measure of if the spatial distribution of something is clustered or unclustered. And the x-axis is r, which is the radius of a sphere. So the K function basically shows the number of earthquakes in ever-expanding circles away from each event. And there is an analytical solution, which is just pi r squared. But the analytical solution only works if basically if your area is a circle, else you get edge effects. So what I did to make these plots, the solid lines, I just created a completely uniform distribution of earthquakes over the area, and then calculated Ripley's K function. And that came up with the solid lines, whereas the dashed lines are my data. If you look at the areas of high strain, my data follows a fairly uniform and therefore Poissonian distribution very well, because they are fairly distributed over the entire region. Whereas for these lower strain rate regions, so these are all times 10 to the minus 8 per year, particularly the lowest strain rate category. The data, which is the dashed line here, that's very typical of clustering. So there's a lot more clustering here than you would expect. And I think this is partly because there aren't so many GPS regions in low strain areas. So if you have a fault there, you might not pick up any high strain rate. It will just show it as low, and yet the earthquakes will be clustered there. And partly it's an effect of the aftershocks, which can continue for a very long time in low strain rate regions. So using this model isn't good if the dashed line and the straight line don't match so well. So that's one way you can try and figure out if your seismicity is okay to use. It's hard to know exactly. Say if you had a lot more GPS, it would solve one of the problems of low GPS, and it might pick up areas of high strain where earthquakes occur. But it's a lot harder to solve aftershocks that just go on for hundreds of years. I think you just have to look at your data and see how it looks. I don't think I can give you a solid number exactly.
No, that was very helpful. Thank you very much.
Thank you. There's another question by G.
Hi, thank you for the talk. It's really interesting. And I have two questions. The first is regarding the parameter alpha, which I suppose is the percentage of a strain being released through seismicity. Do you have a feeling of how well constrained that number is and how well it generalizes over space? And does could it be verified with the aftershocks that we remove from the clusters, for example?
I mean, a simple and honest answer is I don't really know how well it is constrained or how uniform it is everywhere. It is one of the main unknowns, and I did assume some level of aseismicity based on a literature review. But that's something that does go into the equations, and you do need to know. I get if you have a really good earthquake catalog and you have, say, a good coupling model or a good knowledge of how the slip rate builds up, and you see a large mismatch, then you can figure, maybe there's loads of aseismicity. But it's very hard because, like, what if tomorrow there's a super large earthquake there and it ruins all your kind of plans? But I think it's a very large unknown kind of fundamental question. And I know it does seem to vary between different places, but I can't say exactly how much it would vary or how uniform it was.
Yeah, and I guess that might also influence the Mmax that we can get from.
Yeah,
the equations,
exactly.
right?
Like, it's true. Even low strain areas, it was all the kind of low strain rate was just released aseismically. Then yeah, you wouldn't need such a large earthquake to balance that. Yeah, it can definitely vary between the different regions of different strain rate. Yeah.
Yeah. Cool. And I have another question. You mentioned there is potential for applying this method on INSAR geodetic data in the future. And I have been working on INSAR strain rate maps. So I do hope to move on to the seismic hazard aspect using that data set. So with INSAR, we have very good east-west measurements, but then very poor north-south measurements. So do you think there is a way out from this aspect?
I'm not totally sure. I mean, the strain rate maps that I plotted were the second invariant of the strain rate tensor. But it could be, it depends on the geometry of faults, of the faults in your area. Like, yeah, I think it mainly depends on the geometry of faults, whether you're capturing the main strain rate or just a small amount of it. Yeah, I use the second invariant of strain rate, but potentially some other strain rate measurement could be used instead. Like if it correlates with the seismicity, then sure.
Great, thanks for your answer.
Thank you. We have further questions in the chat, and since Olivier had raised his hand earlier, I'm going to read his question first. Thanks for the talk. I understand the logic to say that Mmax doesn't depend on the strain rate, but do we have evidence that large earthquake, let's say magnitude 9, occurred in low strain rate areas?
Yeah, magnitude 9 is a bit high, and it's true. I think Tim Wright said that too. You do need a structure for such a large earthquake to occur. So, I mean, I don't think there's going to be a magnitude 9 plus kind of randomly in the middle of India. That's true. But then in the lowest strain rate regions, this model worked the least well, I guess. Yeah, that's one thing. In the regions of lowest strain rate, the model did work the least well. And I'm not sure how, I don't think there have been any magnitude 9 events in super low strain rate regions, apart from, I think unless there's specific other things going on, like I think in Scandinavia, there was some magnitude 7 or 8 plus earthquakes when the ice caps melted. But yeah, no, it's a good point. I don't think there will be such a large earthquake in a very low strain rate region, but then the model didn't work so well in those regions, yeah.
Thank you. Yes, I think this was also the answer to Tim's question, right? But correct me if I'm wrong.
Yeah, I think so. And I think maybe aseismic deformation might be more important in the lower strain rate regions, perhaps.
Yeah. So I have a follow-up question. So if you're not sure if magnitude 9 earthquakes ever happened in those low strain rate areas, do they actually matter much, or are they so rare that they don't impact the probability anyway?
Yeah, so in the seismic hazard, if you look at what most people look at, the 10% chance in 50 years, it is a fairly short time period. And actually the exact maximum magnitude earthquake really doesn't matter so much, because you're a lot more likely to have smaller earthquakes. Whether the maximum earthquake is 8.5 or 9.5, it might not make that much of a difference, just because you're looking at a 50-year period. And so naturally there's such a lower chance of the 9.5 earthquake. It doesn't really make that much of a difference, but which is very different from different kinds of seismic hazard assessment, like assuming the maximum magnitude earthquake, and then looking at that would be very important. But yeah, in this probabilistic matter, it's definitely not super important.
Thank you. Oh, I just see this was also Tim's question. Sorry. Ekbal.
Hi, Vicky. Thanks for the great talk. I wanted to ask your thoughts on the assumption that strain rates remain constant regionally or even on specific faults. How much would that impact on your probabilistic calculations?
I guess if you are looking at the next 50 years, you're going to assume that it is fairly similar to the past 20 years. And in a way, what happened in the past 1,000 years isn't so important because that was 1,000. Well, actually, no, the earthquakes have been building up strain for a long time. So I guess if the strain rate was higher in the past, then yeah, the moment buildup would be larger than you get from the GPS. So you would expect larger magnitude earthquakes, but it wouldn't shift anything in the seismic hazards in the seismic catalog. That would stay the same. So I think in my model it would just mean the maximum magnitude earthquake would be larger if the strain rate had been much larger in the past 1,000 years, which, as I mentioned before, the maximum magnitude isn't so important. So yeah, I guess the recent seismicity or the seismicity in those 10 years is much more important than how the moment might have changed in the past.
Right, thank you. The further questions? In this case, I have a question. Did I get that right, that with your new method, the hazard map that you computed in general showed a lower hazard compared to your 2018 study?
Yeah, that's, can I go back?
I found it interesting.
It's partly because in my 2018 study, the seismicity was constrained to occur basically along the fault in the strike direction and also on the fault geometry, so it gets shallower towards the surface. Whereas, and how OpenQuake works is it has an epicenter somewhere and then it creates a rupture. So on the right-hand side model, the ruptures are all on the fault plane. Whereas in my study, you might have an epicenter on above the main Himalayan thrust, but it wouldn't be constrained to rupture on the main Himalayan thrust. It could go a completely different direction. So that's why it's a lot more smoothed out. And they also have a certain depth in them. But in my study, they're also not constrained to be on a shallow dip slip fault. It could make a strike slip fault or anything like that, which is why it completely kind of smooths out the strain and thereby decreasing it over the area. So the total strain across should be fairly similar.
Okay, great, thank you.
Sure.
Great, thank you very much. So Vicky, great. It was absolutely fantastic to see you. Thank you very much for the interesting talk. To everyone else, we're going to be putting this online. It'll be on the Earthquakes in Central Asia website. Note that next month we're going to be rescheduling Catherine Fitzsimmons' talk on lake quaternary environments and sedimentary histories in the Tian Shan region, and then also Jean-Francois Ritz will speak at the end of April. So yeah, Christoph's just given you a link to the website where this will be hosted. Thank you once again. That was incredibly interesting, and a goodbye to all of you.
Thanks.
Thanks.
Goodbye.